Hi, today I'll be talking to you about our paper, Cluster Examples in Multi-Dataset Benchmarks with Item Response Theory. I'll give an overview. First, what are multi-dataset benchmarks? What is item response theory? Then I'll talk about how to make IRT multidimensional and the applications for this on benchmark analysis. Then I'll move to talking about how we can correlate IRT features, 1D features, between textual features from either topic models or BERT, and then I'll finish with future directions. So what are multi-dataset benchmarks? For a given task, like NLI or sentiment analysis, it's when we evaluate on more than one dataset. A great example of this is Dynabench that has many tasks and many datasets. In this paper, we use sentiment analysis and NLI because they have simple label spaces, either 2 or 3 labels. Across these, we use SST, Dynasent multiple rounds, Amazon and Yelp reviews, and all the other datasets listed for NLI. Then we also use all the models that Dynabench has. The reason why this is awesome is that we did not have to run any of these models. We just used the already computed dev set results for each of these models on all the datasets, and this is an extremely powerful way to analyze benchmark data. Next, I'll talk about what is item response theory. So IRT is a latent variable model that links these three things. First, items, which are test or dev set examples. Subjects, which are, in this case, models in a benchmark. So all these other little robots here, that's what these represent. And responses, which is whether a subject responded to an item correctly. So all these subjects will assign a theta value, which will represent its skill. And all these items have properties. They can be hard, they can be easy, whatever. So that's what these values represent. And all these combine with this equation, which I'll talk about more in a second, to compute the likelihood that the subject J has a correct response on item I. So in this, we're going to take a closer look. So theta, in this case, is going to represent the skill of the subject, or how good a model is. Beta is the difficulty of an item, or the difficulty of a particular NLI example or sentiment example. The main thing to notice here is that as this number grows bigger, then this entire number grows closer to 1. So when does that happen? So as theta, or the skill of the model, increases with respect to the difficulty of the example, then the likelihood of answering is correct, and this is what we want. So we use several different IRT models, but you can fit these models with variational inference or MCMC methods. But the main problem with IRT in this formulation, the motivation for our paper, is twofold. So one, the parameters, even when we infer them, don't explain why an example is easy or difficult. And examples can be difficult along multiple axes. So for example, a particular example could be difficult because it involves math or geometry and only a little bit of language. And a single dimensional model doesn't capture that nor explain this. So in terms of research goals, first we create a multi-dimensional IRT model, which is not a novel thing. Then we try and correlate IRT 1D and multi-dimensional features to interpretable features. So can we correlate what these IRT parameter values with something that us humans can see, so we can see, this example is difficult because of its features are related, maybe it's more movie reviews than food reviews, and then visualize these correlations. So we take this model from before and make it multidimensional in a very simple way. We make gamma, theta, and beta all multidimensional. So we have a multidimensional minus a multidimensional, and then take the dot product, and that yields a single scalar for this particular equation. In most of our experiments, we make the number of dimensions equal to the number of data sets for that particular task. So moving to our experiments, the first thing that we wanted to ask is, do IRT parameters correlate to interpretable features? And the assumption is that examples from similar data sets, like if the examples from Yelp or Amazon reviews, we take those. They should have similar IRT characteristics, such as the difficulty of the examples along particular dimensions, and thus hopefully they'll cluster together, and we'll see that. So we attempt to correlate IRT parameters with interpretable features by either dataset type or dataset labels, or derive textual information like topic model identities. So our basic method is we train a multi-dimensional 2PL model, so only difficulty and ability in this model. Then we use tsne to project those multi-dimensional parameters into a 2D space, and then visualize the parameters based on either the dataset type or the dataset labels. And the way that we do that is we plot these 2D embeddings and then color either by dataset on the left or by label on the right. And what we see is not what we expected, which is kind of our negative result. Is we expected to be able to clearly see that all the different data sets clustered on their own. What we instead found is that most of the clustering seems to happen according to label instead. So we don't see dataset level clustering, but we do see label level clustering. So the next thought, if the source dataset isn't getting clustered, can we correlate to other features instead? So for example, if reviews tend to be about movies, perhaps those tend to be easier or harder or clustered together. So the method that we tried first is we take topic models, so train topic model on Dynabench sentiment data, and then sanity check that the topics make sense. So these are the topics in our paper. So one's about books, one's about movies, one's about food, and these are pretty sensible. And then how do these correlate to item difficulties? So we analyze the relationship between the highest scoring topic per example. So we take the topic distribution for an example and just take the most dominant topic. And then the difficulty parameter of a unidimensional 4PL model. So we take the distribution of IRT difficulty, which is shown here, and then we overlay this with normalized histograms of, for each example, which topic it's assigned to. So for example, if one particular example had a topic distribution that was dominantly in this green topic or this food topic, then we assign it that. And then we look at, according to difficulty, what's the breakdown in these different topics. So we see some slight patterns that along this lower part of the difficulty, this green topic seems to be easier, food, and slight pattern that on this orange topic, the room or service or people or hotel topic seems to be more difficult, but it's not super clear. It's kind of, you squint a little bit, and this is one of our negative results in the paper, you could say. And then the last thing we checked is, how does IRT difficulty influence BERT? So if in addition to the normal objective, we train a model where BERT predicts the unidimensional 4PL difficulty and discriminability parameters from sentiment datasets, and then we visualize the embeddings of a normal BERT model versus one that is also trained to predict these difficulty and discriminability parameters, do they differ? So is BERT encoding this information coming from the IRT model? And the basic answer is yes. So on the left, we have the normal BERT model that doesn't seem to cluster negative, neutral, or positive labels, and on the right, using those IRT parameters, that it does. This is not too surprising a result because the IRT parameters kind of reveal the difficulty, and it seems like the difficulty of some labels is probably easier than others. Particularly, I believe neutral is a more difficult class. And I'll wrap up with future directions. So the big one is, in all our models, we did not jointly infer IRT parameters in topic models, and I think this will be very important. And part of the reason for that is that multi-dimensional IRT parameters over-parameterize the eval data, and adding text features will make use of those parameters. And along similar lines, joint inference of the IRT model and some transformer language model. And some of the takeaways is our assumption on datasets and topics being separable by IRT doesn't turn out to be true in our experiments. And we do find interpretable clustering on the label level rather than the dataset level. Thank you. And if you want to see our paper and code, we have links here. And if you have any questions, feel free to reach out to either myself or Fu. Thank you.